Yeah, the Trifid Nebula. Let's see. I tried that one a while ago. Now, the exercise that you did is probably one red, one green, and one blue, right? And that's what we'll go over today. One of the things we'll go over today. And at the OPIS level, that's, plenty. In fact, this is one step above what OPIS was intended for, just to give them a taste of color combination, which they find really exciting. Some of them will go forward and do it anyway, whether we included the instructions in the lab or not, they'd just try. So we figured we'd add some optional instructions. But it's also kind of a teaser for the MW course, which is much more serious astrophotography, optical, and radio. Let me see here. Let me find. I think Trifid was one of the early ones I did, so I'm not sure if I did a good job. Yeah, here's some Trifids up here. Yeah, these were early attempts. That's probably the best one I got there. Of course, that's stacking much more than one red, one green. I am sharing, right? Yeah. More than one red, one green, one blue. But it's a
I,
great
I
source.
don't see it. I don't see it then on the screen.
Oh, maybe I'm not.
If you're sharing, yeah.
Oh, maybe I'm not. So let's see here. Yeah, I wasn't sharing.
Yeah, right now I see that. Yeah,
Beautiful.
very
Yeah.
good.
So that may have been a few hours of observing, but in the MW course, the students who MW is really meant for students who have done OPIS. They don't have to have done OPIS, but really they should have done at least one astro course or physics course. It shouldn't be like their first experience with science. I tried that I've offered the MW course twice, and we're still developing the material as we go. I'd say the text is about 85% done, and the videos are about 75% done. So there's still stuff to go. In the first offering, I really enjoyed it, although it was crazy because I probably wrote 300 pages on the fly as I was doing it. But the second offering, I decided to let in a bunch of students who didn't meet the prereq. And for us, the prereq is any astro or physics course. You just want to have some background. But I decided to waive that and see how it went. And I was not really pleased with that population. So some prior experience, and OPIS is a great prior experience. And yeah, we made all sorts of. I had to learn all this astrophotography stuff on the fly. I didn't have that background before. And we've coded a lot of this in Afterglow because a lot of the astrophotography packages out there are the learning curves are really, really steep and not really student appropriate. But we want to have enough enough capability to do some interesting things, not just make pretty pictures, but we then take images like this one here and we'll make measurements, like we'll count the number of bright stars in the region, measure the size, do Strömgren sphere calculations. We do get very physical with it. Something. Let's see, I'll just show a couple others while other people pop in. These are just kind of randomly selected. Here's the Tarantula Nebula. It's the Bean Nebula. It's also up in the LMC, so a little bit harder to image. Planetary stuff. So there's red, green, blue. That's actually just one red, one green, one blue on Jupiter. So you can do that really nice with Jupiter. We do lunar mosaics. So this is each one of these is a 5x5 grid times 3 filters, so 75 images. And we put together software to piece it together. It doesn't always work, but sometimes it does. And these are color stretched, so you can do some lunar mineralogy. It's one of the opening.
Dan,
Yeah.
you mentioned that the Trifid Nebula that you just shared was a stack.
Yeah.
Does Afterglow do stacking or no?
Oh, yeah. Yeah. And we've added a lot of more advanced features for the MW course that we don't touch in OPIS.
Okay.
But if you want to preview some of the MW units, I know I have a better source. 1 second. Yeah, my
Because
chess.com.
that's what I noticed when I combined mine. It was a single exposure of red, green, and blue, and the noise for the sky was a
Hi.
lot. So I
Yeah.
had to put it in a different software to reduce the noise a little bit.
Yeah. There's a little bit of noise reduction you can do in Afterglow, and I'll show some of that. But let's see, I'm going to put this in the chat. This is the MW sign up for this semester. If you're going to be offering it, don't sign up here. I'll send around a new sign up before the next semester. But the top of that page are, let me find it again, are links to the MW modules where kind of the flow, we start with the solar system and here they're learning skills. We have this awesome HR diagrams module with this great tool that we built. And then we get into star formation, the radio universe, one of those units still being developed. Star death, we have 3 different levels. We have like standard pretty picture stuff of planetary nebulae, and one on radio, one on pulsars, and one on LIGO, gravitational wave stuff that's still being written, and then some galaxy stuff in the radio and optical. So it's a sequence that's kind of orthogonal to the OPIS sequence. The OPIS sequence is really about the cosmic distance ladder, following that thread through introductory material. And, if you do teach astronomy as a 2-semester sequence, kind of the fuzzy stuff often gets into the second course, like star forming regions and how they work, and galaxies and how they work, and star death. And so that's in here, and how to interpret color. But 50% of the units are radio, and we also supplement a lot of archival infrared. And although astrophotography is the hook, it's not the point. We do calculations and stuff as well. And it's much more freeform. Right now, these are just links to Google Docs. It's not in WebAssign or Cengage or anything yet. And I'm still shooting videos and still writing. It's probably going to be 2 more years before we kind of release this, but there are already a dozen institutions using it. Anyway, so we were just talking. Jay said he did one of the colored combinations. We're going to do that this week. And so we just started talking about MW stuff. Anyway, let's get back on track. Is it this? No, it's not it. That's not it. I have a window with like everything ready. Oh, it's this one. Okay. All right. So we're going to do a bunch of things this week, a bunch of small things. Let me check my notes here. I am recording. Good. Okay. Last week we did lab 2, the Stellarium version, and as advertised, I added 2 videos about the globe version. The globe version is done more slowly over the course of 2 weeks, though it's really like 1.5 classes to do it. And we used the second half of the second class to go back and do that bonus color image. And that's something we'll go through today. It's just a kind of a slower spot in the schedule, so we do it there. So that was last week. Just want to let you know those other videos are there. And then this week, I'm going to start by showing you how to do that RGB color combination, which is the bonus activity in lab 1. And yeah, I think last time we were talking about the observations they should put in. And one was taking, one of their pretty pictures from lab 1, which they did in high through. So a black and white, but high signal to noise of a nebula or a galaxy or a star cluster. Pick the one they like most and go back and submit red, green, and blue with longer exposure times. I think it was 8/3, 6/3, and 4/3 for blue, green, and red times whatever they did for the high through. And it's just one image of each, but it's just, a little taste of what you could do with color combination. So we're going to do that today. We'll talk about grading, because many of you who are doing this this semester are now wrapping up lab 1, and you probably want to know how to grade it. And then we'll start lab 3. There won't be time to do all of it, but we'll get it going. And in particular, we'll learn how to put in the observation for lab 4, which is the parallax observation. That's kind of the trickiest observation, the whole OPIS sequence. And then next week, our accessibility expert, she couldn't make it this time. She'll make it next time, Kate Meredith of Glass Education. She'll talk for part of it, and we'll do the rest of lab 3 for the rest. That's the plan. Okay. So let's see. The RGB combination. So back to lab 1 here. Back here in the first week beyond the labs, we say, you know, although not required, some students try to make a color picture or two for a few pointers. First, learn how to use Afterglow in week 2. We've done that. And then watch this tutorial video. And it's pretty detailed. It's a 20-minute video. And there are like 3 levels that you can do with your students. Level 1's pretty easy, but 2 and 3 are also interesting depending upon the level of background your students have. And here, you know, we tell them to take your favorite one from above, and here put in a B at 8/3, a V at 6/3 or 2 times the exposure, and an R band at 4/3. Also warn them that these burn a lot more credits, so be careful. Though, you know, if your students really eat up all their credits because they were doing astrophotography, then they shouldn't worry. I've given you extra credits, and you just give them more credits. And if you run out of credits, let me know and I'll give you more credits. You know, if a student runs out of credits because they're having fun doing this stuff, you want to encourage that, not penalize them for using all their credits. That's your future astro or physics major. So, you know, lean into it. And then there will be a page, I don't think it goes anywhere yet, where we're hoping to create some kind of photo bucket or repository where people can dump their images with some description. I don't think I've set that up yet. Okay. So how to do this. Now that video, you can also find it on the Skynet University page under Lab 1 Week 2. You go to the full playlist. It's this bonus thing down here at the bottom. And I demonstrate with the Omega Nebula, and that's what I'm going to use again today. Okay, so here I am in Afterglow, and I searched around and just found 3. You could do this with I like demoing this with the Nebula because the level 3, the more advanced version of this, involves dust correction, and often you can see that with nebulae. You can also see with galaxies. But anyway, I looked for the same images that I used in the demo video with the same object. I think they're different images. And let's see, what do we have here? Here's the B, and what was this? This was taken on prompt mechering, so it's a 1K by 1K. These will process, you know, they're small, so they're going to process a little quicker. If you're doing 2K by 2K, you know, expect it to take 2 to 3 times as long to process. And what was it? This was a 200-second exposure, so this is kind of on the hefty side. Here is the green, and here's the red. And the red has some H alpha in it. The green one has some O3. And with CCDs, you tend to get better signal to noise in the red. That's why we do the longer exposures in the B. As we transition over to CMOSs, it's going to kind of be the other way around, most likely. Okay, so I'm going to walk through the steps here. And again, there's the detailed video, so if you don't follow everything, it's okay. Here we're looking at the B. And the first thing you may notice are these speckles. These are hot pixels. And there are also cold pixels in here, places that are artificially dark. These are just bad pixels on the detector. When you do a bias, dark, and flat correction, they don't correct. And normally the way this is done is you would get like 5 to 10 at least, maybe tens or even 100 images in each filter. And when you align them and stack them, you could do some statistics, some outlier rejection to get rid of those things. But here, this is just a single image. So my for his undergrad thesis, came up with this really nice cosmetic correction algorithm. It removes individual pixels and also columns. And that's right here. So the first thing you do, often when I'm doing this, I like to just have those images the only thing in my file list. So I often recommend delete everything else, but you don't have to. You'll see why in a second. So I'm going to go to cosmetic correction. And if they're the only things in my file list, I can just press this button and select all. Otherwise, it's a drop down. You hunt through and find the images that you want to correct. And I'm going to submit this. It only takes a moment. It's a lot faster than it used to be. And there. See how all those hot pixels disappeared without really impacting the rest of it. And he wrote a great honors thesis. I wished he had written it up as a paper, but he ran out of time. But it's a nice little algorithm. It's really, professionally, you'd have bad pixel masks or, the stacking and outlier rejection. But for education, you often just have one image. So it's a nice bonus. Okay. Removes that kind of shot noise. Okay. I'm going to mute you, Christopher, just because we're getting some noise. I tried to, I can't, but okay. Next we align. That's the next tab down here. And again, I'm just going to select all three. You have to pick a reference image. It does not matter which one. The other two will be aligned to it. And I think by default, all of these are on right now, and that should be fine. If they all came from the same telescope, you don't have to worry about scale and skew. They're using the same detector, though there can be rotation from image to image because gravity tugs on the telescope differently. And you want to crop because when we turn these into a group, an RGB group, they have to be the same size. And you can use the WCS for alignment. If I move my mouse around here, you can see the coordinates down at the bottom of the RA index. There are actual coordinates there. If you don't have RA index on your image, well, you probably didn't. It's probably a crappy image. All these should go deep enough that you have enough stars that Skynet should be able to add a coordinate system. And we're using that coordinate system to align. And so I'm going to submit. Okay, they are aligned. You have to click on each to reload them. But you may have noticed before as I hop between them, they shifted a little bit, but see, there's no shift anymore. They are aligned. Okay. Next thing is we're going to select them. This is select all, or you can select them individually. And under the triple dots, you group selected files. Okay, this makes them a single FITS file. This is now a multi-layer FITS file. FITS files can have layers. And if I click on the top, the group level, this is a combination of all three. Now they're all black and white at the moment. So the next step is to color them. I'm going to right click on the B1, color it blue. Right click on the R1, color it red. Right click on the V1, color it green. Okay, so that's not a bad start. We're still not through level 1, but you can see how this is pretty easy to do. And the goal is to make this easy. If you have to load PixInsight or all these other fancy software packages, the learning curve is just too steep for students. And particularly here in OPIS, where this is just a taste of what's possible. It does a lot more, and you'll see that in the MWU curriculum. Okay, so level 1, we're gonna, so we have to go over here to the display settings, and we're gonna link them all, the 3 layers together. So when we change the brightness and contrast on one, it changes it automatically on the others. And it doesn't matter too much which you pick for the linking. I usually pick the red one, but it doesn't really matter. I usually pick the red because it's usually the highest signal to noise one. With CCD cameras, you often get the best imaging in the red. So I use that as my base. You can see its histogram here. These are the histograms for all 3 layers. This is the number of counts in a pixel, and this is the number of pixels that have that number of counts. And you can see this is logarithmic. So, it's really getting high here. And so we have a lot of pixels with small number of counts, and those are the background. And then you have a smaller number of pixels with large number of counts, and those are the stars and the nebula. Okay, so you pick your reference. I picked red, and then you go over here to color composite tools. And the first one is our level 1 activity. link all layers percentile. Okay, it won't change the image because that was already the default assumption, but now they're linked. Here in the red layer, like if I go to another layer, like green, I don't have the brightness and contrast controls. It just says it's linked to the red one. If I go to the red one here, I have these brightness and contrast controls. And so these are some of the basic things you can do. You have a background level and a saturation level. So here's for red. Here's the background level. Here's the saturation level. And we're in percentile mode, so it's in percentile. So the background level is 10%, the faintest 10%. We go up 10% in the distribution. That is what we're going to color black. Anything beneath it is also black. And then the saturation level, we're going 1% in from the top. And that's totally adjustable. Like I can raise the background level and you'll see how the background gets darker. Of course, you can go too far and it looks kind of over processed. The rule of thumb is to get it just a little bit below its peak, you know, if you want to get technical. So, oops, I'm going up still. Let me bring it back down. So it's right there at the peak. Maybe I'll lower it to 25%, just a little bit under the peak. And that's kind of the ideal rule of thumb setting for getting a good background without it looking over processed. And then the saturation level is the bright end. If I lower this, then you see more and more of it saturates. Anything above the saturation level is just pure white. Put back the default background of 25. Okay. Now the other control you have is the stretch mode. These are 16-bit chips. The CMOSs are 14, but the CCDs are 16. There's more dynamic range in the image than you can display, than the eye can see. And we have these different stretch modes we use in OPIS: linear, log, square root, hyperbolic, arcsine. And some are good for bringing out the faint end, but you just kind of blast out the bright end. Some are better at looking at the bright end, but then the faint end's too faint to see. You can kind of see the effect here. If I zoom in, see how that star is just kind of, it's not actually saturated in the observation. We didn't saturate the detector. It's just a brightness and contrast. Those pixels are part of the 1% that's above the saturation level. You can see if I increase this such that that doesn't look horrible, I'll bring that down to kind of a better looking star there. Then I've lost all the faint stuff. So there's this extra mode that we use in the OPIS course called midtone. So I'll go to midtone here, and you got to hit the default. And midtone's nice because it adds a box in between these two. And it's done so you don't blow out the bright end and you can still see the faint end. It's like the best of both worlds. Now I'll probably increase that background again to the peak there. Saturation you can leave in place, and then it's a matter of playing with the midtone level. If I increase this, it's going to dim the faint stuff, focusing more on the stars. Or if I go in the other direction, I can really bring out that nebulosity, but without blowing out the stars. You see the stars still stay good as that continues to go down. I'll put it back to the default. Okay, so that's the level 1 RGB combination. A little bit noisy, but it's only a single image, and we did the cosmetic correction and got rid of some of that shot noise. Okay. All good so far? Okay, level 2. Percentile combination isn't guaranteed to get the colors right. It's going 1% in from the top of each distribution, and that may not be the same appropriate level. And so the stars may not have correct colors, the nebulosity may not have correct colors. If basically it's making an assumption that the bright end of this distribution corresponds to something white. And you know, some stars are redder, some stars are bluer. If you have a distribution of stars dominating the bright end, on average, they're pretty close to white. So it's not a terrible assumption, but we can do it correctly. So to do it correctly, this is level 2. We come over here and link the pixel values. At first, it won't be right. See, we have more counts in the red band than the blue band, and more in the blue band than the green band, just because of exposure times. The color here is being dictated by how long we exposed in each band. But you start by linking the values, and then we're going to calibrate the values. And that's down here under photometric calibration. And normally it loads in your files by default. I was messing with it, so maybe it didn't, but put in the red, the green, the blue. Reference layer usually picks the red by default. And then what you do is you press this button, measure 0 points. What it's doing, it's extracting every star from each image and calibrating it against the OPIS catalog. And that sets the appropriate relative layers. Here you see the 0 points and their difference. This is, well, it's magnitude, so it's a backwards logarithmic scale, but the differences here set the fractional coefficients of the green to the red and the blue to the red, since we set the red as a reference. I'm going to set extinction to 0. That's the default. And playing with extinctions, the level 3 activity. But the rest you don't have to worry about. The white balance is a statement about how the human eye works. The human eye will see a black body peaking in blue as white, strangely. If there's a black body that peaks in the blue, the human eye sees it as white. And so you have to, there are different color balance options. We normally just leave it there to mimic what the human eye sees. And calibrate, and there you have the actual colors very close, approximating that the R, V, and B as the very close to the filter response of the human eye, which is not bad. It's very close. So these are the colors you'd actually see. And the stars are a little bit redder than what we saw before because there's a lot of dust along this line of sight. Everything is redder than what you saw with the percentile because there's dust reddening everything. And that's level 2. And again, you can play the same games with your mid-tone stretching or whatnot. I'll just leave that alone. Then level 3 is correcting for dust. And if you want, you can go and look up the EB minus V value. Some are poorly measured. At this level, I just tell the students to play it by ear. So here's photometric calibration. Dust along the line of sight will scatter out the blue, reddening it. And so we can take that out. It's nifty. It's like, I call it color focus. And so this is a very physical approach. You don't see this in the amateur market packages, the thing like Photoshop, PixInsight. They what they do is they change the definition of white balance. They change the definition of white to get the good colors. Here we're taking a more physics-driven approach. It's red because of dust, and so I've programmed in, or my programmers have programmed in dust extinction curves, and we can remove the dust. And I don't know, let me take out too much dust for starters, a full magnitude. EB minus V, that is the magnitudes of extinction in the B band minus the magnitudes of extinction in the V band. And so if there's a full magnitude difference between those, there's a lot of dust. And if I do that, it will overcorrect it. Things got too blue. All my stars are kind of blue now. Yeah, and so you can play with it till it feels right. I'll do, let's try 0.5. And that feels pretty good. Look at the stellar colors. I got some blue stars. I got some red stars. The nebulosity is a combination of bomber pink. The bomber sequence is, you have H alpha, which is red, but then you have some green and blue ones that make it a little bit of pink. And oxygen 3, which is kind of a greenish blue that's mixed in here as well. And in giving kind of a white color in combination with the H alpha. There may be some silicon 2 in here as well. Sulfur 2, sorry. And that's red. But anyway, that's level 3. And so depending on how much time and how much detail you want to go, level 1 is quick and easy. And but then you can get fancier if you want.
Hey, Dan.
Yes.
So I know on the WebAssign you, when you do level 3, you have a table that shows the different extinction corrections that you can do.
Right.
If myself or other students want to explore other celestial objects or deep sky objects, I guess where can you find those extinction corrections?
Yes. those extinction, you can find, so that table that's in the video, now we've now incorporated those objects into the lab. And so that's why we don't use that external table anymore, it's temporary, but you're right, we haven't put the EB minus Vs in the lab. I think you go to something called WebDA. And where is it? I think this is mostly for star clusters though. Then you can pick a star cluster. What we're doing, we're doing M17. And GC 6618. Maybe with the space. They're not all in here. And that's kind of the problem. The EB minus Vs are scattered across the literature. Some aren't measured. Some there's great discrepancies. The tool that we built for the MW HR diagram tool is actually doing a better job of measuring these things than what has been in the literature. And so we've actually expanded that tool to be a self-contained catalog so students can publish their results at the same time. Strange. Okay. That's why at the OPIS level, I'm just kind of leaving it as a free parameter. They can adjust it till they get a nice distribution of stellar colors. Now in the MW course, we take it to much higher levels. So this is just a taste. So if your students like this, you know, maybe point them to the MW course if you all decide to offer it at some point. Eventually, we'll offer it online as well. Okay. That was our first activity. The students get real excited about making a color image. It's worth finding some time in your lab sequence to go through this process. Okay. Questions? Next up, grading. Okay, so let's see. Right, so we'll start here. We'll go to WebAssign. Let's say we're going to grade lab 1. So you go to scores. Wasn't this slow, but there we go. Oh, it's trying to log. Okay, I've been logged out too long. Let me log back in. And this page does take a moment to load. As I said before, I have almost all your sections here. Okay, here's mine. Now I'm going to go to the score view. Okay. And so my students are finishing up lab 1 now. It looks like most of them have done most of it, though we gave them an extension. I often do that with lab 1 because they underestimate the amount of time it will take to actually complete the report, or some of the observations, maybe they put them in late. And so I go right up to the due date and time, and just like an hour or so before I say, guess what, extension. But they then learned the lesson the hard way. They were sweating, panicking, and then they like you even more for the extension. And but then, you know, they know that these are not trivial labs, do them a few hours before kind of thing. Okay, and so here, this is broken into 2 questions where each question has a lot of questions. This is week 1. And remember, in week 1, there were no points to be had. And then week 2. So we go to grade answers. And in this one, since there are 2 questions and there are no points in the first question, I'm just going to grade the second. So I don't have to keep scrolling through that first week of material. So I'm going to start grading. Okay, so this is the first student, last name begins with an A. They're alphabetized out of 32 in this particular section. And we just see the section, but then we can see we're in answer key mode. So a place where you can put a score and comment. And again, as much of the lab as possible is auto-graded. But in lab 1, there's a lot of manual grading to do, and also lab 2. But with each progressive lab, it gets easier and easier. More and more is auto-graded, less manual grading. But lab 1, there's a fair amount of manual grading. So we'll spend a little bit of time, and I'll walk through some of the considerations. Let's see. This semester, my students were able to get everything except Venus. And usually it's only half. So we got like the grand tour, and that's great. Let's see, let's open their first one here, Mars. Let's see if they did a good job. They did not zoom in. So that's one of the things we ask them to do in the lab is to zoom in. Not that Mars has much detail. It will early next semester, late this semester, early next semester, we're closest approach, but we're not close enough to it yet. Really, within about a month of closest approach, it gets big enough to see some detail. Let's try one with more detail, Jupiter. Like for that one, I would have given two out of 3 points. And I'll explain the points in a second. Yeah, they forgot to zoom in again, but yeah, not bad. Okay, so how do you grade these? We have a grading guide. You don't have to use it. It's just there to help if you want it. I'll put it in the chat. It's the grading guide. Each lab has a separate tab down here. We're on lab 1. And I'll probably spend some time in this time, but I won't come back to this for the other labs. You'll get the idea. The top, we have some stuff about cheating. I'll come back to that, and the EXIF viewer that you should put in your browser. You can get for free here. Anyway, just a reminder, you click on scores, grade answers, select the second question, click on start grading. And then these are the parts that are not auto-graded, the parts where you have to do some manual stuff. It's usually if there's a short answer, an image or a graph, those, or a calculation, those are the things that you have to go in and do some. Well, most calculations are graded, actually, but if they're showing their steps for a calculation, that's when you have to go in. That's like a short answer. So let's start going through these. We'll probably do maybe 2/3 of these until we have an example of each. So the first thing was the images that we were just looking at. WebAssign, I have it set up for 3 points per image, and these are my recommendations. Subtract a point if they didn't zoom in. That student didn't. Subtract a point if they didn't set the brightness and contrast correctly. They did do that. We looked at Jupiter, I could see the detail on the planet. So they must have used something like bright target. But if they did like default or faint, it would have been just a blur of sky glow. Subtract a point. If it's streaked, subtract a point. They could have re-imaged. Now, some students may have pulled out an extra object in twilight. Maybe something was close to just being barely observable, and they're smart and changed the air mass constraints or the sun elevation constraints and pulled something out that the others didn't get. I tell my TAs, I give them extra points for that. Good for them. Also, this is something we can check for cheating. I guess maybe I'll explain the EXIF Viewer Pro right now. It's something free you can load into your browser. Mine's right here. And as you're grading these labs, where was lab 1? Here it is. No, I'm down here in grading. So let's pull up that Jupiter image again. If I right click, I can click show the EXIF, and this one does not have the information. Not sure why. Let's see if some of the others do. If they did a screen capture of their screen, it won't have it. Let's check here. This doesn't have it. It's sad. Just got go to another student. Maybe the student was doing screen captures instead of using, so if they save it using this button right here, then it will write a couple things into the EXIF, the JPEG EXIF header, when it was done, who the Afterglow user is, and who the observer of the data was. I was meeting with my TAs this morning, and I found one that did work. Let me go to the next student. Maybe this student was not doing it correctly and was using doing their own screen captures instead of that snapshot. Let's check out their Jupyter. Oh, colorized it. That's cool. Show EXIF data. Here we go. Under EXIF, there it is. It's right here. And I think once you open it once, you'll remember it for future uses. Afterglow access, here's when it was done. The artist, that's what's it's listed under, but undefined, it means when they set up their account, they didn't fill in their first and last name, but there is their Skynet username. And here is the name that's in the FITS file, the observation. So you see the Afterglow user and the observer, when it was done. And between that, that's like a 1-click or 2-click way to check cheating. And is this user Cash Dunker? Good. So submitted their own work. Anyway, if there's an opportunity to check for cheating, it's listed here in bold. Let's keep, and if you have questions at any point, just let me know. Let's see, what else is in this lab? We scroll on down. We ask them to describe what they saw. Down here, we do have the observation ID numbers. They're not worth any points, but if you want to go look at their actual observations in Skynet, just load up one of your own in the URL, switch out the ID number, and then you can see the data they took. Okay, and then here are the descriptions the student gave. And here's the answer key. And what's it say here? Up to 3 points per detected object, use the key. PB2, we have a table. So that's procedure B, part 2. Oh yeah, here's this table where they're filling in, did they observe it or not, telescope, date, time, and then the measured angular diameter. And you will know, which objects your students could observe. Sometimes they'll fill stuff in for something that wasn't observable. That's why we can't use the autograder here. We don't know which objects are going to be observable ahead of time. So it autogrades in each cell, but then you kind of do a tally and put the score here. So the grading guide recommends 5 points for filling in the telescope and date info, then 5 points for sufficiently correct angular diameters. So for the observable objects, it's all check marks, so 5 points for that. And then here, they're graded very generously. We're not using an ephemeris. It is, I know how small, angularly small and large these things can possibly appear, including generous atmospheric blurring, and just checking if it's in that range. Apparently, Uranus, they measured something too high. I bet they forgot to put it on bright target settings, and so they actually measured the sky glow instead of the size of the planet. So here they got 1, 2, 3, 4, 5 out of 6. So 5, 6 times 5 is the number of points they would get there, added to their 5 over here. So they got, almost 10 points. And you can modify that and put in a comment. There's another table here. Here they're measuring the angular diameter from stellarium and computing a % error. And see here they type something in for Venus, and we're not counting Venus. So that's why you have to do it manual, ignore anything that wasn't observable. And looks like they got these all correct from Stellarium. And with percent error, they got one wrong. And then this one here, they calculated it correctly, but the input was wrong. So if the inputs are wrong, they get the wrong answer. But if they did the calculation correctly, they have this special symbol calculator. And so what I do in the guide here, I tell them to add up the number of checks and calculators and scale it to 10. So I would count that. We had 1, 2, 6, 11 out of 12 times 10. And so that's what goes there. You can add comments. Now, a note about the calculators. In other labs, we'll see the calculators as well. And WebAssign gives 0 points for the calculators, which I don't like, because you can make a mistake early on, and then you go farther and farther into a calculation, and you're doing all the calculations correctly, and you've already paid the price for measuring something incorrectly at the beginning. Should you lose all the points through all the steps because of that? I say no. So if there's calculators, I usually figure out how much it was for and just add it into the closest box. Unfortunately, WebAssign, there's no setting where I can say make the calculators count for points. But here, we're tallying and giving the points. Sample calculation. This is the percent error calculation where they're showing their work. And so that's also in the grading guide. Things, common things they forget to do, like forget to multiply by 100 or forget the parentheses, or they have a negative percent error. And so those are things you can subtract points for. And then there's a discussion of sources of error. And this, I encourage you to grade these particularly harshly. So they are motivated to improve their sources of error discussions. Even though we tell them you can't say human error, measurement error, calculation error, because you can always go back and recalculate or remeasure or find a human to help you. Those are not valid sources of error. We're looking for things that are limitations in the ability to make measurements. And in the guide, it says, give them a point if they mention anything about atmospheric blurring. Give them a point if they realize that the small objects will have high percent errors because the atmospheric blurring is many times the size of the object. The large objects will have small percent errors because the atmospheric blurring is a small percentage of the object. Atmospheric blurring is a couple arc seconds. We have objects ranging from half an arc second to like 40 arc seconds. So if they pick up that effect, give them a point. And then they comment it's difficult to measure the size given the blurring, atmospheric blurring, and pixelation of the image. And so in the observing guide, grading guide, those are recommendations. Almost there. Let's see, what else? Again, I'm not going to do this for every lab, just this one here. Moon identifications. So here they've uploaded their images. Let's see how this student did with Moon ID. It's loading. Okay, so this one, they loaded the Uranus image in the Jupiter slot. Let's see what they stuck in the Uranus slot. Maybe they got the images backwards, or maybe by accident they image it. That's Uranus. Maybe it was the Saturn. What was that? Let's go back here, that Jupiter image. Oh, 1 second. No, no, that is Jupiter. They didn't tilt it. That's it. So they have Callisto. They say this is Io and Europa. This one's normally they're pretty straightforward. This one's confusing in all sorts of respects. But anyway, the point is they have the date and time. I recommend grading this on a dual monitor display if you can. You put Stellarium up on the other monitor, you turn off the ground, turn off the atmosphere, and you can just hop from planet to planet very quickly, have the date and time window up there. You can adjust it to this, and very quickly you can check their moon identifications. I grade these pretty leniently. But in the guide here, I say subtract a point if they incorrectly ID something or if they miss something. 0 points if they gave you incorrect time. Like if you can't match up with, very quickly, I wouldn't give them any points. But I'm pretty generous because sometimes they're background stars that are in the image and they can get confused and call them moons. And then the facts about each moon. In section 5, we do the dwarf images. Dwarf planets. Let's see how they did with Pluto. We'll load up Pluto here. This one's worth 3 points, one for getting the right field, one for circling reference stars, and one for IDing Pluto. And then we can bring up the DSS. Sometimes it helps to view both at the same time. So sometimes I'll make a little copy there that I can bring back. And here's the DSS one coming in. And I could bring this back and yep, looks like they did a great job, full credit. Palmia and Maki Maki are tougher. And that's pretty much it. The rest are just, did they make their pretty picture look pretty? 2 points. Let's see. This was their star cluster. Looks good. Okay. And then, when you're done, you can save it and move on to the next student and work your way through. And again, it gets easier from lab to lab. This one just has a lot of images and identifications you have to check. And so there's a fair amount of manual grading in this one. Questions about any of that? Okay. Let's see, lab 3 and the lab 4 observation. So, at the beginning of lab 3, we put in future observations. Let's go through the lab 4 observation and we'll save lab 3 for next time and see how much we can get done with the accessibility piece as well. So lab 4 observation. Lab 4 is the parallax lab. And this is the trickiest observation to put in. This is one that you're going to put in one for the entire class. And you've been granted special target opportunity access to be able to submit this observation. So now in here, I have a tutorial that you should watch on how to do it. And it's tricky because you're trying to get simultaneous observations from a scope in the south and a scope in the north. So you can actually see the parallactic shift and measure the distance to a main belt asteroid. There's other parallax observation measurements they do in this lab. But this is the one thing they observe. The others are archival. We always try to observe something. So I do have some hints. If we go to the observing guide that's at the top of each lab, look at the hints for lab 4. 2, 3, 4. So it tells you, what section in lab 4 to go to. And here's the video that explains it in detail. And since you, the instructor, are doing it for the class, you'll want to watch that. It's tricky. If you don't have target of opportunity access, email me ahead of time and I'll grant it to you on some southern scopes and some northern scopes. You need the target of opportunity because to achieve the simultaneity of the 2 telescopes, you need to be able to trump the whole system. So target of opportunity gives you priority over everyone. And I try to be very clear, you cannot abuse this. You can use it for this. Don't use it for anything else. If you use it as a matter of course, you're going to lose your access. No, I've never had to do that, but that, got to make a threat, right? Instructor should put it in. They should do it in front of the class so the class can see how it's done and they feel ownership. That's one of the things that come out of the education research. Them taking their own images creates ownership. This is the next best thing. If you do it in your office before class, they're not going to feel ownership over this data. But if you do it together, it's at least halfway there. You got to watch the weather at the sites you choose because if you want to pick a night where it's going to be good at both sites. Normally you have a backup site in the north. In the south, we use Cerro where it's good like every single night, except during our summer, their winter. And so that one's almost guaranteed to go through. And then you pick 1 or 2 up north and keep an eye on the weather. When it's done, it will be in your directory. So the students will go into Afterglow, into Skynet and group, and then they'll find your account and you'll direct them to the particular observation and which exposures to use. And then I say here, if your instructor utterly and embarrassingly fails, do not fear. There's data in the sample directory. And that's just me gently prodding you to actually submit the observations instead of relying on the sample data. You could rely on the sample data. It's just not as exciting for the students. But it is a tricky observation. So you should give it a go. You may have to do it 2 or 3 times and to get it to work. And the other times you can put those, if it fails the first time, feel free to resubmit them in your office, not in front of the students. Just the initial one, they should observe it. Okay, so next is how to pick the target. I have 5 minutes. I could probably do this in just a little bit over 5, but let's see here. In the lab, we point you here to the Wikipedia page of exceptional asteroids. They're ordered by diameter. We tell you to start down here at Davida, or Davida, I don't know how it's pronounced, but below 300 kilometers. These other ones are too bright and would want to do shorter exposures, and it becomes too like serious. You have to do like the exposure would be too short to even have background stars to measure, to align the images to measure parallax. So we start down here, and then we check them in Skynet. And you may have to go through quite a few, but this semester Davida actually works, so this will go fast. I'm in Skynet. I'm going to add a new observation. First one on the list that I'm checking is Davida. Okay, found it. Let's see, I'm going to start by viewing it from Tololo. I'm going to hit the Now button. There's the sun getting ready to set, and so it comes up second half of night, but it's up for a long period of time. There's the sun rising. So, maybe somewhere around here would be ideal, but we also have to make sure that it works in the north. And so for that, the best site to check would be Sleaford. That's our Saskatoon site right here. And I check, and at that same time, it is up. Maybe I'll go forward another hour here and go back to Tololo. So very observable at Tololo. And Sleaford's a little low in the sky, but not terribly low. 10, 20, 35 degrees up. That's fine. And so we're going to go for this. So the next thing you do is you look at the time. It says it's going to be around 5 a.m. Eastern time. You kind of want to move them both to as close to the middle of the sky as possible. 5 a.m. Eastern time. So you write that down. 5 a.m. We're in daylight savings time, so that's 9 hours GMT. Greenwich Mean Time or Universal Time. Okay. Let's get our numbers here. Minus 12, 20, and 0.5 are the standards. I want to check if the moon's not anywhere hovering around here. It's not. That's good. Okay, I'm going to choose my filters. I believe we're using high through. It's in the lab, but if I recall correctly, it's high through. And for target of opportunity, you can only submit one at a time. So in the south right now, prompt 6 is the functioning telescope. We're working to repair the others. So I selected prompt 6. And this one, we don't pick the generic. We use prompt 6, and we're going to do 15 40-second exposures, 10-minute block. And we're going to have it start at 9 GMT. And then we're going to resubmit this on USask and have it begin at 9 GMT. And they'll be at the TO level. If we come down here, we click on this target of opportunity, it's going to trump everything else, but it will finish the exposure that's going on. It may take different amounts of time to slew, so they won't actually start at the same time. That's why we do a block. And as long as there's some overlap, there's going to be one image between both blocks taken at the same time, you're going to be okay. So 15, 40-second in the native telescope scaling. We want to flag it We're going to delay the start of the observation. And let's see, today is the 26th. So let's say it's the 27th at 9 UTC. And then what I do is I copy this and paste it down here for cancel and set cancel for 10 minutes later. So if this telescope is weathered out, there's no point taking it later because the other telescope won't be taking it then. So it's a 10-minute window, target of opportunity. And before submitting it, you want to check the weather. I'll probably go like 3 minutes over. I'm almost there. So we have links to the different sites. Here's Tololo. And the weather's good. Great. And then kind of my other site that I'm going to use, I'll give you a handful of ones in the north, and you may want to put them in on multiple systems just so you have something that comes through. But our canonical is Prompt Saskatoon, and it looks like it's going to be cleared tonight as well. So great. So here we go. I'm going to submit it. Oh, I've got to pick a time account with some credits. Submit. And as soon as it submits, I'll resubmit it on the Saskatoon telescope. Okay, so here it is. I'm going to click on it. I'm going to resubmit it. Go back to telescopes. And I'm going to turn off prompt 6, and I'm going to turn on prompt USask. Save and continue. Prompt USask 15 40-second exposure, so also a 10-minute block. Target of opportunity. And for whatever reason, the cancellation always resets to a month out. So, set it to run on the exact same time. Save and continue. Save, and it's in the system. Kind of rushed a little bit at the end, but there's a video on it. And it's tricky. You could get weathered out at one site, so maybe put in 2 in the north. It's almost always good in the south. And hopefully it works out. If not, you just go and hit the resubmit on all of them, changing your time frames. And get it back. And then you have to, when you get it back, this is the last thing I'll say since I'm over, you see which one started second. One will start earlier, one will start a few minutes later. The one that started second, find that first exposure and when it was taken. Go back to the first observation and find the exposure that's taken about the same time. And then you tell your students, okay, in Afterglow, don't go to user, go to group, go to my folder, go to these 2 observations and grab the 0th and the 4th exposure. And they're synchronous or near synchronous observations. And when we do lab 4 in a couple of weeks, you'll see what they do with them. But that's how to put the observation in. Questions? All right, then.
I have a question.
Yes.
Okay, I tried this a couple of times in the past few days, and almost always my observations gets cancelled. Does this mean it was overwritten by something else, or
No.
I checked the weather?
Did you select the TOO option?
Yes, I did.
It must have been weather.
Okay, yeah.
So maybe check the weather at the sites so you have some expectation. You may have to do multiple sites in the north to guard against weather. It can be tricky. Of course, if there's bad weather at Tololo, then it's no good either. Make sure your start times and cancellation times line up and that they occur at times that are observable at all the observatories. That's why it's tricky. There's a lot of timing stuff. But here you just saw an example. Davida is a good one for 9 hours universal time. So I guess that's my recommended asteroid. That one should work.
Okay, thank you.
Anything else? And of course, there are ones in the sample directory if it doesn't work out. Okay, we're over. I'm going to let you go. And I'll put this up on the YouTube site, and I'll see you next week for Lab 3 and accessibility.
Thank you, Dan.
My
Hey,
pleasure.
Dan, real quick,
Yeah.
have you seen Vladimir or talked to him recently?
Yeah, I talked to him online yesterday. Has he not answered your email?
Not yet, but I realize he might be busy. I just was setting my own expectation.
How old is your email? When did you send it to him?
Oh, that's a good question. Hang on.
It's been a day or two. Just send it again and CC me.
Okay, it's probably been closer to a week than a day.
Oh, okay. Send it again and CC me. You know,
Okay,
I'll nudge him.
sounds great.
Okay.
Cheers.
See ya.
Yeah.